Hello! In this episode of Finno-Ugric Machining, we are going through the analog to digital conversion in the microcontroller environment. In this case, we have 3 channels for the potentiometers. Well, if you are not interested in microcontrollers and if you are not especially interested in programming, this is the place to stop and start watching something else. So, let's start with the thing. So this is my short presentation of analog to digital conversion in a microcontroller environment. Okay, next slide. There. So these are the components of a typical analog to digital conversion system in a microcontroller. First of all, here in the left you can see 3 channels, because we are now talking only about this application. We are using 3 channels for the potentiometers. So the next component in the signal path is the multiplexer. The multiplexer is taking the correct channel for conversion. It selects one channel at a time to be converted. Well, there is a good reason why we are using a multiplexer in a microcontroller. You could probably, yes you could, slap in 8 couples of analog to digital converters in one microcontroller. That would, for the first, make the current consumption quite a bit greater, and then it would also make the circuitry quite complex, etc. There are some benefits of doing it this way. Okay. The only drawback is, of course, the speed. It will be slower because you convert one channel at a time. Well, there has to be a place for this analog to digital converter to put the result into. There is a dedicated register for that one. Yeah. The result will be there after the conversion is ready. Then we have this interface, which is used by the program code. The program code will access all these components through the interface. You can find a specification of this interface in the microcontroller datasheet. There are some programming environments support you with modules which are dealing with this analog to digital conversion. Well, what I have found out is that they are not optimal. They usually, what they do, they don't use interrupts. You will soon notice how nice it will be to use the interrupts here. And furthermore, they don't they are somewhat slow. And because of not using the interrupts, your program code will be involved into the conversion process, which is not very nice thing. Okay, the next slide. From here on, I'm describing the conversion process, and these slides will always surround the involved elements with a yellow border. Okay, the first step in any microcontroller environment, if you are going to use any subsystems from that microcontroller, is to initialize it. Whether it be, as in our case, the analog to digital converter, serial interface or something else, you have to initialize it. Tell the microcontroller how you are going to use it. So, of course, the instructions will come from your program code, and you set the multiplexer, analog to digital converter, and probably also empty the result register. This is always the first step. Luckily, it doesn't need to be done multiple times. It's enough to do it once. Next slide. Well, now we are starting the conversion. First, you have to choose the channel which is converted, channel to be converted. So your code uses the interface to set the MUX multiplexer in a way that it will read channel 1. Okay. Next slide. Now, when you have chosen the channel, you will initiate, start the conversion. So, the analog to digital converter starts the conversion reading the multiplexer. It doesn't read directly the channel, it will read the channel through the multiplexer. And at this point, if you are doing this in an interrupt, you will stop here, go back to your original program and continue there. This has to be done outside the interrupt when you are doing this the first time. It will be obvious in the next slides why is that. Okay, now next slide. After a while, this microcontroller, it takes some time to do the conversion, but when the analog to digital converter is ready, the first thing it does, it stores the result in the result register, and if so programmed, it will interrupt your program. This means when there will be an interrupt, it will stop whatever you were doing in your main program. Store all the program status, store all the registers, you can choose which ones, but usually you store them all. Then it will jump into a service code for this interrupt. Okay? So your main program will be stopped, and then the execution of the program code starts in interrupt service routing, ESR. There, in the interrupt service routing, you will read the result register first, of course. You will read the register, and then you will output your result in a suitable place for later use. In our case, we have 3 memory locations where we store channel 1, 2 and 3 results. So, that's basically it. This is the first step. The next step in the interrupt code, in our case, the interrupt code will actually initiate the next conversion. So it will choose now the next channel, boom, through the multiplex interface, and sets the multiplexer in a way it will be reading channel 2. Okay, next slide. And the next thing it does, it initiates, starts the conversion. Now, at this point, the interrupt code, which was servicing this conversion, will end, and the program will return whatever you were doing in the main program. Restores all the registers and starts execution from at the point it left off for this interrupt service routine. Then you just continue doing whatever you will be doing in that main code. Next slide. And now you were doing whatever you were doing in your code, and please notice that this analog to digital conversion doesn't happen in a microsecond. It doesn't, maybe in a millisecond, but that's a really long time in a microcontroller environment. So what happens next is that when the analog to digital converter becomes ready again, it will interrupt your code, all your code registers will be saved again, and the code jumps into the interrupt service routine. Okay. Next slide. Well, what you do there is, of course, you read the result, and in this case, because where you were converting channel 2, you will store the result in your memory, which is dedicated to this channel 2 value. Okay. And finally, you of course select channel number 3 and then start the conversion and exit the interrupt routine, do something whatever you do, and get interrupted again. And when you get interrupted, you will be starting at the beginning of the channels, channel 1, 3, and so these channels go in a loop 1, 2, 3, 1, 2, 3, etc. And using this sort of interrupt based conversion, interrupt based conversion control system makes the conversion as fast as it is possible in this kind of environment. Well, it doesn't hurt your program performance unless the analog to digital conversion is really, really fast. But in this case, it's not. And you can slow it down a little bit so that you have time to do your own stuff in the main program so that the interrupt doesn't steal all your time. Okay. This is the basic functionality of the analog to digital conversion in a microcontroller environment using interrupts. Now, let's look at the code. Now, let's see how a typical program code looks like. So, here we have a very typical program code. This is part of a library I have created. It contains definitions for the microcontroller itself, and so that it's not you don't need to use some magic numbers or probably some proprietary code from Atmel in this case. So the first thing, if you look here carefully, this part here, this one is just telling the system what kind of reference voltage you are using. Are you going to use reference outside the chip? So the internal reference should be turned off. Or are you using the plus 5 volts VCC? Okay. Then you use that option, or probably the band gap reference inside the chip. but then you need to be really careful to adjust your own reference in a suitable way. Okay. So then you have all sorts of, you have actually 8 channels, but these can be arranged in a multitude of different ways. Well, for simplicity's sake, we are using the single-ended channel. So there is only one wire for each channel, and then the value from that wire is measured. So that's the simplest option. Of course, there are some differential inputs, gains, and whatever. We don't need that. And then if you are using, my library also allows polling. So if you are using polling, so what this means is that instead of using this fancy interrupt, you are actually every now and then checking from the analog to digital controller, you are asking, are you ready? Okay, you are not. I'll do something else. Are you ready? And you do this in a loop, and when it finally gets ready, then you do something with the result. And these are what will be done when it really is ready. The first option is that it will actually initiate right away the next conversion and returns you the result. The next one is to get the last result and then initiate the next one. It's both are usable, but we don't use this because we are using the interrupt. We get there in a moment. And then these 6 functions here are all that you need to know. Initialize your system, and then set the scan range. We are using that one. Also, first channel to read and the last channel to read. Okay. And then last but not least, enable the system. If you just initialize it, it doesn't do anything. You have to enable it separately. You can also disable it if you don't need it more. This is needed in battery operated systems where current consumption is a deal. You want to minimize that one. So now what we are using, 2 more functions, is the scan set, as I told you, first last channel, and then channel get. And this one you can get any value of any channel. Okay. So how do we use this type of thing? So the first thing I always do when I create a program, I create a header file specific for that particular application. In this case, this code is for induction heater control system. And this one has, for example, here we have what is the frequency you are using when you operate this, etc. There are some defines for ports, etc. And then somewhere here we have the analog to digital channels, and well, this one is reading it's using all 8 channels in this case. It's this system has 4 potentiometers and 4 other type of channels, temperature sensors, etc. And then you have a lot of defines. This is something you probably don't need to know because it's not for this application. So, in the main code, this is now the main code. The first one, this is just to include the application specific header, and then these 4 here are just setting the port input-output configurations correctly. Initialization, hardware initialization. Then we have a thing called the watchdog. At this point it should be enabled. This is something that will reset your code if it's stuck somewhere. Well, we are humans, we make mistakes, always. And then the next here will enable the interrupts. Now we have some timer subsystem which we initialize here. Well, here we initialize the analog to digital conversion. What we are using here is this one is using 8 millisecond intervals for each channel. So it's not too fast. You shouldn't do it too fast. And then we are going to use in this case also the 5 volts. Okay. And then we set the scanning range. Well, you remember the interrupt starts always after last channel, it reads the first one. So this one configures the system in a way that when it starts with potentiometer 1, and when it reaches the current, when it has done with that one, it will start again from the beginning. And after that one you can do whatever you want in the program. The analog to digital conversion happens in the background. The data for you is always available there. You don't need to wait it anymore. And well, this is just a very normal mine loop. You always do things in a loop in a microcontroller environment, and I do it in this way. There is one analog to digital task, some lamp task, probably taking care of blinking lamps or lighting them all the time or whatever. And then we have fun task. Well, this is code for induction heater, so there will be a fun because there is a cooling system. So actually running a coolant. So you need to there is a radiator and a fan. So this fan is controlled with PWM actually. So it doesn't run blow by full power all the time, only when needed. Pump task, this is also etc. This is not applicable to our application, but the system, how I will do this is quite the same. Okay, this was a quick sneak peek into the code. How do we deal with that one? So I will go into more detail the next time we will have an episode for this VFD speed modulator. So this was that. Next time we do some programming on the main loop. We see how to arrange things, how to set up things. Till then, bye!